Chapter 7, Section 1. Here we go. We're going to graph exponential growth functions. I know. Stop groaning. It's graphing. You can do this. Here we go. Exponential growth functions look like this. So the y equals a to the bx. So b to the x power. So the exponent is our x. And in order for this to be a growth function, the a has to be greater than 0, so no negative numbers there. And the b has to be greater than 1. So it can't be a fraction, it can't be a negative number. This b has to be bigger than 1. And just so that you are aware that b is the growth factor. That's the number that's going to be taken to the exponent. As with all of the graphs, I'll show you a parent function. If you can get in your mind what the general shape of this graph is, then this really won't be hard. We just graph 2 points and then you know the shape of the whole graph. So the parent graph looks like this, where it starts very close to the x-axis. It goes through the point 0, 1, and then it's going to go through the point 1, b. So b is your growth factor here, the number that has the exponent on it. So those are the 2 points that you'll need, and then you know that it's going to go closer and closer to the left to the x-axis, and then it's going to curve up quite quickly, because you know when you take something to an exponent, it gets bigger and bigger very quickly. So that's the shape of your parent graph. One vocabulary word that you will need to know is asymptote, and did I use that? I don't know if I used it or not, but this line, this x-axis, where this to the left, it's going to get closer and closer and closer. It's never actually going to touch that x-axis, and it's not going to cross it. That is an asymptote, a line that the graph comes closer and closer and closer to, but never quite touches it. That's an asymptote. So in this case, the x-axis is the asymptote of our graph. Let's do some. So first, let's look at, y equals 3 to the x power is the very simplest form of this y equals b to the x power. And just for the sake of looking and seeing where this shape comes from, let's graph several points. So if you take 3 to the negative 2 power, remember that's going to flip it down. So it's going to be to the 1 over 9. Negative 1 just flips it, so that makes it 3 to the negative 1 power is 1/3. 0, remember anything to the 0 power. Do you remember? Anything to the 0 power is always 1. So that's why you'll always go through the point 0, 1, because when you put 0 in for that exponent, it's going to make that whole, that b equal to 1. Anything to the 1 power is itself, so 1, 3, and that's where you get the 1b point. 3 to the 2 power, so 3 squared is 3 times 3 is 9, and 3 cubed is 27. So when you graph these points, negative 2, 1/9 is right there, negative 1, 1/3 is right here, 0, 1 is right here, 1, 1, 2, 3 is about right here, 2, 9 is way up here, and 3, 27 is way up high off of your graph. So then you can put a smooth kind of ish curve through these. Oh, goodness gracious. You know how to do it better than I can. Here we go. So that's where this curve, this shape comes from. So now all you'll need to do is, if you graph these 2 points, the 0, 1, that'll be an easy one to find, and the 1b, or the 1, 3 in this case, and graph those, and then zip, make a lovely smooth curve. Make it smoother than mine. All right, that will give you your exponential growth graph. Now, when we put an a in front of this and we make it y equals a b to the x power, still your y-intercept in this case is going to be your a. All right, so instead of 0, 1, you're going to have 0, a, because when you put 0 in and this is 1, when this is 1, then 1 times a is what you end up with. So the y-intercept is going to be your a. The a is going to be going to tell you whether the graph is going to stretch or shrink. Okay. So the a stretches or shrinks the graph, and if it's negative, it's going to flip it down below the x-axis. Now, one thing to note, if you have a negative a and it flips below, remember then your a is not greater than 0, so it's not a growth function. It's not an exponential growth function. It's still a function and it's still a graph, but we don't call it an exponential growth function. And it'll be obvious when we graph one why. You'll see if it's not growing, it's falling. Huh. So here we go. So let's look at a graph like this. If you can remember the parts and pieces and what it looks like, it's going to be very, very simple to graph. So the y-intercept is a, so the y-intercept is 1/3. So you've got 0, 1/3, the point 0, 1/3. And let's see, and then we're going to have, if we put in 1 for this, 1 for 3 to the 1 power is just 3. And 3 times 1/3 is 1. So we have the point 1, 1. And then we know that the curve is going to look like that. So we're done. That's really all you need to do. So you put in 0 for the x, put in 1 for the x, and then just graph it. All right? This is what's going to happen if it's negative. Here we've got the a is actually -1. -1 is multiplied by that 7/2. So the a is -1. So now we've got 0, -1. And our b is 7/2. And so when we put in 1 for the x, when we put in 1, we get 7/2, but then that's a -7/2. So we've got 1 for the x and 7/2 is 2, 4, 6, 7/2 is right about there. And so now this graph, because it's flipped, it's going to get closer and closer to the x-axis, but underneath it. So it's going to come this way and then zoom, go that way. And you'll see that it's not, we can't call it an exponential growth function because it's not growing. It's not getting bigger. So this is what this function looks like, but we don't call it an exponential growth function. All right. Let's see. So step 1, put in 0 for your exponent. Step 2, put in 1 for your exponent. Graph both of those points and then graph your exponential growth function. That's it. So, of course, I have to make it more difficult. We're also going to, what if that's not exactly where it starts out? What if we have a slide? And you know that's what I always do. Let's move things around. So a translation is another word for a slide. And this is what that graph will look like. If you have y to the a, b, and if you'll look, if you cover up this part, it's exactly what we just did. It's that y equals ab to the x power. But if we subtract something from our x and then add a constant, now we've slid that graph up or down or left or right. And so just like in the other graphs, the h is our horizontal slide, so right or left, and k is our vertical slide, up or down. All right, so the steps to do that is simply to graph it as if it didn't have that h and k. Just graph it, and you can even leave it on your graph if you wish, or if you want to just graph those 2 points and then move them, that's okay too. So graph the original graph and then slide it. All right, let me show you what I'm talking about. Here we go. And this is on this graph, so I don't know if we can have both of those at the same time. So here we go, and I'm going to come back real quick and look and make sure that you can see the top of that. Yes, okay. All right, so here's our function, y equals 4 times 2 to the x minus 1 power minus 3. So if we were to just graph 4 times 2 to the x power, what would that look like? Well, let's look. We're going to have, if we put in 0 for x, that's going to be just 0, 4, because this is equal to 1. So 0, 4, 1, 2, 3, 4. So we're going to have a point here. And then if we were to put in 1, ignoring the h and the k, if we were to put in 1 for the x, then we have 2 times 4 is 8. So we have 1 over 8 up. 5, 6, 7, 8 is right here. All right, so this would be the original. So if I was going to graph just y equals a to the bx, did you see what I did? I ignored this minus 1, minus 3, and just graphed it just like I did these over here. So then, and I didn't actually write the graph, that would be a lovely little curve that you know I can't do very well, but I want you to do yours perfectly. So this graph is going to come up like this, but I'm not finished. This graph has a horizontal slide of 1. And now this is where it's tricky. The H, remember, is the opposite of what it looks like. So because this is a -1, I'm actually going to go +1. So each of these points is going to go to the right 1, and it's going to slide down 3. Because the K is your vertical slide. So we're going to go to the right 1 and down 3. So from each of these 2 points, we're going to go to the right 1 and down 1, 2, 3. So here's going to be my new point. And this one's going to go to the right 1 and down 1, 2, 3. And so here's my second point. Now the tricky thing is you've got to make sure that you have the right asymptote. Okay? So my asymptote was the x-axis because that's where it started. That's where it always is if you don't have an H and a K. So because I moved down 3, 1, 2, 3, my asymptote now is -3. So y equals -3 is my asymptote. Okay, so this this line of -3 then becomes my asymptote. So it comes up. Oh dear, I have to draw this lovely line with you watching me, and my graph doesn't make it easy because these little lines are not smooth, and I'm blaming it on that. What do you think? Will that work? Okay, there we go. So this is my new graph. You can see the original one would have been right here. So what's happened is I've just slid it over 1 and down 3. So now when I ask, well, what is the domain and the range? The domain, remember, is the x's, and the range is the y's. So the domain is all real numbers. So the domain is all real. And the range, though, is the y's. And if you'll notice, these y's, they can't go below this asymptote, this y equals -3 line. So the range is y has to be greater than -3. So does that make sense? So this graph can have any x. It can go this way, it can go that way, it can go anywhere on the x's, but it cannot go below the -3. So the range has to be greater than y greater than -3. Alrighty? So far so good? All right, now, let's use this information in real life situations. So we're going to use the exponential growth model. All right, this is another one of those you're going to need to write this. You're going to need this, this equation. Y equals A times the quantity 1 plus R to the T power, where A is the initial amount and 1 plus R is going to be the growth factor. Let me show you what I mean. Oh, you know what? I didn't erase yet. I'm getting so excited. Okay, so this has to do with the growth of, we're going to do it with population growth. You can do it with, yeah, I was going to say with mouse growth. Oh my, I guess that's population also though. Ew, let's not talk about it. Okay, so we're going to talk about the population of people. So we're going to use this exponential growth model to talk about the population in Kern County, California. In 1970, they did a census, and the population was 330,000. And then from 1970, so this was the census in 70, from 1970 to the year 2000, they saw a growth rate of 2.4% annually. So what we want to do is we want to use this information to first write a model for what is the population growth, and then 2, find the population in 1990. And this is simple because we have an equation. Oh my word. So what we're going to do is use the equation. Y equals A1 plus R to the T power. So start out with the equation and then plug in what you know. The A is the initial amount, so that's the population that we started with, and that's the 330,000. And then, oh, I'm going to have to move this over, but that's okay, I can. Here we go. Make sure it's not out of the picture though. All right, 1 plus the rate. So the rate is 2.4%. So remember, we got to change that to a decimal. So we got to move the decimal 2 places to the left. So 1 plus that is going to be 1.024. And the amount of time is going to be the number of years that we're talking about. So for the first question, write a model demonstrating that growth rate. Ta-da! That's all you have to do. Easy sneezy. Okay? Now, once you get that equation, then if I want to know, well, what is the population in 1990? All I have to do is, well, I have to plug in how many years. So y equals 330,000 times 1.024 to the t power. So from 1970 to 1990, 70, 80, 90, is 20 years. So t is 20. Now you're going to say, oh my goodness, that is a huge number. You're right, it's a huge number, but your calculator can handle it. So what you're going to do is you're simply going to take this information and plug it into your calculator. If you've got a simple iPhone or a phone calculator, that works. And I don't know if it'll work on the, let's see. Oh man, what am I doing wrong? It's easy if you know how to do it. There we go. There's a calculator. If you turn it to its side, and I don't know if you can see it, you've got all the extra buttons over here. So what you're going to do is you're going to first put in the 1.024 and use the X to the Y button. It looks like this, X to the Y button. And you're going to push that and then push 20 and then get your answer. You push equal and get the answer, and then take that number, whatever that is, times 330,000, and you should end up with about, so the population is going to be about 530, and it's more than that, but we're going to round it. For something like this, you don't get very specific, and definitely don't do decimals because you can't have a portion of a person. All right, so if you have one of the scientific calculators that you probably already know, you put in this number, and then that button is just a caret. So you put, oh, that's a Y, not a 4. You put a caret and then the 20. The caret is the exponent button for those calculators. Okay. Easy, 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 easy. That's all you have to do. So use that formula. You need to know that formula, but once you know it, you just plug in the numbers. So that's so easy. I'm going to give you another formula. And this one you've probably used before. I know you've done simple interest. This is compound interest, which is more fun if you're the one putting your money in, because it grows faster. All right. So for this one, the compound interest formula is A, it stands for the amount that you're going to have at the end of the allotted time. A equals P times 1 plus R over N, all to the NT power. Whew! That simply means this. You're going to take P as your principal. That's the amount of money that you start with. The R is the interest rate. And the T is the number of years. That's the same as with the I equals PRT. You know that part. The N is the number of times that it's compounded per year. So if you're going to compound this every month, then this N would be 12. If you're going to compound it quarterly, then this N would be 4. And so all you have to do is know those 4 pieces. You can just plug them in and you got it. So let's do one. Ta-da! Dun-dun-dun, magic trick. Oh my goodness, look at there. All right, so get our equation. A equals P. Oh, I got the marker that doesn't work. 1 plus R over N to the NT power. So once you know that formula, now we just plug in the amounts. And I'm saying we're going to deposit $5,500 at an interest rate of 3.6%. I want to know what is the balance after 2 years. And I want to decide, am I going to compound this semi-annually or monthly? And I want to know the difference between the two. So really and truly, you just plug in numbers. So for the first one, so A equals, the principal is 5,500 times 1 plus the rate is 0.036 over N. Now for the first one we're going to compound it semi-annually. Semi-annually means twice a year. So you put that over 2. And we want N, which we just said was 2. and t, which is the time, is 2 years. So 2 times 2 is 4. So you're simply going to plug those numbers in. Do that right now. I already did it. So while I'm finding it, you plug it into your calculator. What I would do is I would start with the fraction, put 0.036 divided by 2, take that answer plus 1, take that answer and either use your x to the y button or your caret button and take it up to the 4 power. Get that answer, take it times 5,050, so 5,500, not 5,050, and you should end up with $5,906.82. You will need to round these because we don't use portions of pennies. So there you go. So that's your first answer. If you can work faster than I can and do the monthly, go ahead and do that. All right. Let's see if you end up with the same answer. So now we're going to do the same problem again, except that we're going to change the number of times that we compound it. Everything else stays the same. Our principal stays the same. 1 plus the rate. The rate still stays 0.036. The number of times that we're going to compound this now is monthly. So that's 12 times in a year. And so now we're going to do it for 2 years. So 12 times 2 is 24 times that we're going to compound this interest. And now when you plug it into your calculator, once again, 0.036 divided by 12, that answer plus 1, that answer to the exponent of 24, that answer times 5,500, and you should end up with $5,909.97, which is a few more dollars than if you only compound it twice a year. All right, so really and truly, the hardest part about it is going to be remembering that crazy formula. So it's principal times rate to the exponent of the time, but you got to do crazy things with the rate. All right, I think you can do this. Here we go. I'll see you later.